Welcome to Module 18, Building Pressure and Critical Spaces. In this module, we move from general airflow theory into rooms and buildings where pressure relationships protect people, process, products, and operations. The most important idea is that pressure is not created by a sensor or a set point. It is the result of supply air, exhaust air, return paths, transfer air, leakage, doors, wind, stack effect, and time. In a critical space, a small pressure relationship can determine whether air moves into a room, out of a room, or unpredictably between spaces. Our goal is to verify the required airflow direction, understand what creates it, and design BAS alarms that lead to the right response. By the end of this module, learners should be able to explain pressure relationships in plain field language. They should understand why supply, return, exhaust, transfer air, leakage, and doors all contribute to room pressure. They should be able to identify where positive pressure is used to protect a space, where negative pressure is used to contain a hazard, and why a pressure cascade is more than a group of set points. They will also learn to question the measurement chain. A low-pressure transmitter may be calibrated and still report the wrong relationship if the reference location, tubing, range, or door condition is wrong. Finally, learners will design alarms that tell people what failed and what to do next. The core concept is that pressure is a balance. The BAS may modulate a supply damper, exhaust valve, fan speed, or terminal airflow, but the room pressure is created by the full physical system. Supply air pushes into the space. Exhaust and return air remove air. Transfer paths and leakage allow air to move between spaces. Doors create large temporary openings. The adjacent reference space may be stable, unstable, positive, negative, or affected by the building envelope. The pressure transmitter reports the result of those conditions. It does not create the condition. This is why a BAS professional must read pressure, airflow, doors, mode, and adjacent space behavior together. Air moves through openings because of pressure difference. In normal building pressure control, the values are very small compared with duct static or hydronic pressure, but the consequences can be large. A few pascals or a few hundredths of an inch of water column can influence whether air flows from a clean area to a less clean area, from a corridor into an isolation room, or through an envelope leakage path. The direction matters more than the number alone. When troubleshooting, ask, what is the required airflow direction? What pressure relationship should create that direction? And what airflow paths support or defeat it? Positive and negative pressure are not good or bad by themselves. The correct relationship depends on the mission. A positive room tends to push air out, which can protect a product, patient environment, or sensitive process from contaminants in adjacent spaces. A negative room tends to pull air in, which can help contain contaminants or hazards within the room. The BAS professional must not copy set points between applications. A clean room, isolation room, laboratory, pharmacy, and operating room may each have different criteria, responsible authorities, door behavior, and response procedures. Start with the required direction and the governing criteria. A pressure cascade creates progressively different pressure levels between spaces. The diagram uses illustrative values only. Real values depend on the application, door behavior, leakage, safety analysis, and governing criteria. The important training point is that a cascade is not achieved simply by typing set points into the BAS. The airflow pathways and envelope tightness must support the desired relationship. If doors are undercut incorrectly, leakage is excessive, exhaust is unstable, or the reference space is moving, the cascade will not behave as expected. Always verify the physical path that supports the pressure relationship. Critical spaces are not all the same. An operating room, isolation room, clean room, laboratory, pharmacy, archive, or data room may have different requirements and different consequences of failure. The BAS does not decide the mission, it supports the mission. Before editing a sequence, determine what must be protected, who defines the requirement, what conditions must be maintained, and what the team must do when the space is outside the approved state. This is where BS practice becomes operational practice. The correct technical answer must also fit the clinical, process, quality, safety, or operations requirement. Whole building pressure changes throughout the day. Outdoor air, exhaust, relief, wind, stack effect, elevator movement, door operation, envelope leakage, and weather all matter. In tall buildings, stack effect may be strongest during cold mornings. In windy conditions, a reference location near the exterior can become unstable. In buildings where exhaust systems start before supply systems, the building can become negative even though the BAS graphics look normal. Troubleshooting critical space pressure must include context. The point value on the screen is only one part of the story. Measurement confidence is critical in low-pressure applications. A transmitter can be calibrated and still report the wrong relationship if it is connected to a poor reference location. Range selection is also important. If the sensor range is much wider than the expected room pressure, useful resolution may be poor. Check high and low ports, tubing integrity, moisture, kinks, labels, zero, scaling, trend behavior, and reference stability. When a pressure value appears suspicious, compare it with airflow, door status, adjacent pressure, and mode. The BAS professional must verify the installed measurement system, not only the device specification. Doors are one of the most important disturbances in pressure-controlled spaces. With the door closed, airflow usually moves through defined leakage paths, undercuts, transfer openings, or designed relief paths. When the door opens, the opening can be large enough that the pressure relationship temporarily collapses or reverses. That does not automatically mean the control system failed. It may be a normal door event. The training question is whether the room recovers properly after the door closes, whether the alarm delay is appropriate for the hazard, and whether the response procedure reflects actual workflow. Direct pressure control can be unstable if it fights every door opening or every small disturbance. In many critical spaces, a better concept is airflow tracking with pressure trim. First, measure the relevant supply, exhaust, return, and transfer flows. Second, maintain the intended airflow offset. Third, use room pressure feedback as trim or verification, not as the only control signal. Fourth, define limits, fallback behavior, and alarms. The goal is stable airflow direction and reliable response, not a pressure loop that hunts. Pressure control must be coordinated with ventilation, noise, door forces, energy, and safety requirements. Critical space alarms are part of the operating procedure. An alarm should not simply say room pressure alarm and leave the operator guessing. It should identify the room operating mode, failed relationship, door condition if relevant, alarm delay, required response, and escalation path. Delays can reduce nuisance alarms, but only when the delay is approved for the hazard and workflow. Alarm priority should reflect consequence, not just the point type. The goal is not more alarms. The goal is actionable alarms that help the right person respond at the right time using the right evidence. Consider this field scenario. A clean room alarms intermittently every afternoon. The room airflow and doors appear normal, and the pressure transmitter is functioning. The hidden issue is not the room sensor. The hidden issue is the reference space. Outdoor wind changes corridor pressure through an envelope leakage path, so the room sensor reports a changing relationship. The reading is real, but the reference condition is unstable. The correction is not to hide the alarm or tune the room more aggressively. The correction is to stabilize the reference condition and then verify the room pressure relationship under representative operating conditions. Pressure control can appear simple on the screen, but many failures create false confidence. A set point does not prove containment or protection. A calibrated transmitter may be wrong if the reference location is unstable. Door status and workflow can explain short pressure excursions. A sensor range that is too wide can make the trend look stable while hiding poor resolution. Aggressive direct pressure control can hunt. And most importantly, changing pressure relationships in critical spaces may require clinical, process safety, industrial hygiene, quality, or operations approval. Professional BAS work protects the mission, not just the graphic. Use a repeatable diagnostic method. Start with the required airflow direction and the responsible authority. Identify the criteria and the approved operating state. Then verify supply, exhaust, return, transfer air, leakage paths, and door undercuts. Check the sensor range, zero, tubing, and reference location. Test door events and recovery under representative conditions. Finally, validate the alarms and the response process. This method prevents the team from solving a pressure problem as if it were only a controls problem. It also creates a record that another professional can understand and verify. Best practice is to commission the relationship, not only the point. Define the required airflow direction, pressure relationship, responsible authority, and consequence of failure. Verify airflow quantities, leakage paths, door behavior, sensor range, reference location, and tubing. Control from stable relationships rather than chasing every door event. Make alarms actionable, mode-aware, and tied to approved response. Document the criteria, test methods, responsible owners, and results. The final commissioning question is simple. Can we prove that air moves in the required direction during normal operation, door events, mode changes, weather changes, and alarm response? For the knowledge check, the best answer is C. A calibrated transmitter does not eliminate reference problems, door effects, adjacent space instability, or airflow path issues. Do not raise a set point or replace a device until the pressure relationship and measurement chain are understood. For the assignment, the learner selects one pressure-controlled space and prepares a one-page review. The review must show required airflow direction, supply and exhaust paths, transfer openings, leakage paths, door logic, reference location, alarm trigger, alarm delay, response owner, and one safe test with acceptance criteria. This turns the chapter into a professional field workflow. This module reinforced that pressure control is really mission protection. A pressure value is not the whole truth. It is the result of airflow relationships, leakage, doors, wind, stack effect, and time. Positive pressure, negative pressure, and cascades must be tied to the application and the approved criteria. Measurement confidence depends on the reference location, range, tubing, zero, door condition, and trend plausibility. Finally, critical space alarms must be actionable. They should tell the responder which condition failed, in which mode, what evidence to review, and what action is approved. In the next module, we will strengthen our ability to defend engineering calculations and design reviews.